So the next few slides will address Objective 1, describe the formation of the Earth and the distribution of critical elements on Earth. So as you can see by the title here, Earth's resources were determined when the planet was formed. That's an important statement. What that means is that all of the materials that make up Earth from the beginning are essentially still the same materials that we have today. There's very little input. Once in a while, an asteroid will strike the Earth and contribute some material, but 99% of what we have is what existed when the Earth was first formed. Okay, so this diagram shows that there was a consolidation of cosmic dust cloud into a sphere, and that was true of all the planets. And as they formed into spheres, it was a molten material, a hot, rocky material. And as it cooled, this material separated into layers, with the denser layers in the center of the planet and lighter materials toward the crust of the planet. So heavy elements such as iron, still to this day, make up the innermost core of the Earth, and lighter materials such as silica floated toward the surface. There were even some gases which then left the Earth's surface and became part of our atmosphere. So next we're going to look at how these layers, what the result of these layers was, what it looks like. Okay, so now we're looking at the layers of the Earth. There's a lot on this slide, so let's just walk ourselves through it. First of all, let's look at the diagram on the left. Here you can see that there are 4 major layers of the Earth. The first one is the solid inner core. That's surrounded by a liquid outer core. That's surrounded by the thickest area, which is called the mantle. And then there's a very thin part on the surface called the crust. So, looking at the vocabulary terms over here, the core is the innermost zone of the planet. It's made largely of nickel and iron, and it's a solid. It's a solid when it's in the middle, and it's a liquid when it's along the outer portion of the core. So why is there a liquid outer core and a solid inner core? It largely has to do with the pressure. The amount of pressure on the inner core makes that nickel and iron, even though it's so hot that it would otherwise be liquid, it makes it into a solid. Then you move out to the liquid outer core because it's again so extremely hot that this material is melted and it has a little less pressure being put upon it. So the mantle, M-A-N-T-L-E, is above the core, and it contains magma, which is molten rock. So the rock is also still so hot that it's very liquidy. But you'll see later there are layers within the mantle. Okay, the next layer up is the crust. That's the outermost layer of the Earth. It has distinct chemical characteristics. There are certain chemicals that are in there that we can measure and that are distinct to the crust. Now, there's an overlapping term called lithosphere and another overlapping term called asthenosphere. And we'll look at those on the next slide. But just take your attention for a moment here to look at the scale or the size of the various Earth layers. So the inner core, very small, inner and outer together, fairly large, mantle, very significant. And then you can see a diagram, which we'll come back to, of the lithosphere and the asthenosphere. In short, the asthenosphere is the upper portion of the mantle. So it's still part of the mantle, but it's the upper portion. And the lithosphere is a combination of the crust and the very, very top of the mantle. So let's take a look at that on the next slide. I guess we're not. We'll go back to the slide then. Okay, so the difference here with the asthenosphere is that it's semi-molten instead of just molten. So molten means very melted rock, not quite liquid like the outer core, but very liquid rock. With the asthenosphere, it's semi-molten, so it's not quite as molten. If as a kid you ever made oobleck, where you can roll it along in your hands and it stays solid for a minute and then goes flat, the asthenosphere is a little bit more like that. The lithosphere includes the upper asthenosphere. So by the time you get to the upper asthenosphere right here, it's actually become a solid, but it's still considered part of the mantle. And you combine that upper solid asthenosphere layer with the crust and you get the lithosphere. So to recap, you have the inner core, solid nickel and iron, the outer core, liquid nickel and iron, the mantle, which is molten rock, which goes from a very much more molten rock to a partially molten rock or semi, the very top of the mantle being solid, the crust being solid, and the lithosphere being the term for crust plus the very top or solid part of the mantle. So overall, even though the material that makes up the earth is not going to change, there's not going to be significant inputs or outputs from the earth, it doesn't mean that the earth is static. In fact, it's changing constantly. So we'll look at some of those changes, including the tectonic plates, which will be up next. So Earth is not stagnant, it's dynamic, which means constantly changing. And it changes through these three processes, or they're called cycles, but they're really not cycles, they're processes. The first one is the tectonic cycle, the second being the rock cycle, and the third one being the process of soil formation. So the tectonic cycle, again, not really a cycle, but a process, is the breaking down and rebuilding of the lithosphere. Remember, the lithosphere is the crust of the earth, which is very chemically distinct, plus the upper part of the mantle, which is the solid part of the mantle. And that particular region of the earth is constantly broken down and rebuilt through the tectonic cycle. The tectonic cycle includes moving of tectonic plates. It includes earthquakes and volcanoes. So we'll look at those processes next. To recap what the rock cycle is, again, it's changes in rock from one type of rock to another type of rock. This is due to changes in temperature, pressure, water, or wind. Again, it's not really a cycle. And the last process we'll look at is soil formation. That's when minerals, rocks, and organic matter form soils, and these soils have different characteristics. And the process of soil formation occurs through other processes known as weathering, erosion, and deposition. Okay, so now we will look at the process of the tectonic cycles, and we'll begin on the next slide. Again, there's a lot on the slide, so for now, don't worry about all those words. Let's just take a look at the diagram here, which is a cross-section of the Earth. So you can see here that there's crust. Continental crust means the crust, the outermost portion of the Earth that is above water. We also have oceanic crust. Let's see, we can see that right here under the ocean. It's a solid, but it's underwater. And then below that, we have the asthenosphere, which is the upper portion of the mantle, which is semi-molten. And then we have the bulk of the mantle here. And what I want to point out is that the mantle, the semi-molten rock, moves in what are known as convection currents. So the semi-molten rock here, the molten rock here, is not just sitting there in one place. As it goes from the center of the earth where it's warmer and it comes toward the surface of the earth where it's cooler, hot rock rises just like hot air rises. And then that pushes the other rock or displaces the other rock, and you get movement in these cells. These are convection cells or convection currents. And some areas, the hot magma actually comes up close to the surface of the Earth or even through the surface of the Earth. So one of those areas is shown here. It's called a spreading zone. So the molten material comes up very, very, very close right to the edge of the oceanic crust. And as it does so, it pushes the oceanic crust in two different directions, some of it going this way and some of it going that way. So another thing that can happen, that's by the way called a spreading zone. Another thing that can happen is the molten mantle can come up very closely through porous areas of the Earth, and it can even go all the way through to the surface of the Earth, in which case it's a volcano. It can be an active volcano that the mantle is coming up and spewing right out onto the surface of the Earth. So some other things that can happen, let's turn attention over to here, how there is a spreading zone and it's pushing the oceanic crust this way. When the oceanic crust is pushed this way, it eventually meets the continental crust. And something has to happen. And what happens usually when the oceanic crust is pushed toward a continental crust is, whoops, let me go back, is that the oceanic crust has to dive underneath the continental crust. Well, it's not really diving, I guess pushed underneath continental crust would be a better term for it. That's called a subduction zone. And the oceanic crust is then pushed into the mantle where the rock that made up the oceanic crust starts to melt again. So this model of the Earth has been documented, and we'll take a look at how that's been documented. But for example, there's a spreading zone right down the middle of the Atlantic Ocean, and the rock is indeed being pushed apart. It's pushing the North American, South American continent this direction, and it's pushing Europe and Africa in this direction. There are also areas where it's known that volcanoes exist and are very active, and that's called the Ring of Fire, and that's been well studied as well. So we're at 12 minutes on this video, so I think I'm going to pause it here, and we'll continue with the theory of plate tectonics on a different screencast.